let's continue with the fun stuff. Basically, going to talk about my own experiences with F#, how I see it. You know, what is the ethics? So a lot of people, when they hear F#, they go like, man, you know, whatever, dude. Because quite frankly, you know, if you take a person from the street and you show them, well, not from the street, you take a developer from the street and you tell them, you know, here is F#, the first thing they say, oh, look, tool support. Like, what's going on there? Because to be honest, like Visual Studio support is very thin. It's very thin and it's not really improving. You can't even make folders inside your F# project, which I guess for some people is okay. But you know, as your stuff grows, it becomes tedious. There's no code analysis per se, unless of course you're analyzing the compiled intermediate language, which is not what I'm talking about. I guess I'm talking about things like ReSharper. So Visual Studio itself does try to analyze F# to some extent, although it doesn't offer any refactorings or, you know, context navigation, that kind of stuff. And of course, then you get issues with profiling and unit testing because, well, to some extent, once again, if you use something like FSUnit, ReSharper will run the test correctly, but it's kind of hit and miss, and it doesn't seem like people care that much. Then there is the question of market penetration. You know, how widespread is it? I mean, you could argue that it doesn't matter, but you'll still be interested in the statistics, and we know it's thin. We don't know how thin, and I'll talk about why in a sec. And I looked, and it's actually not in the top 50 in the TIOBE index, which I know some people are not big fans of the TIOBE index, but we don't have, you know, like an objective measure of how many people use F#, and once again, the reason why we don't have an objective measure is partly due to the nature of the organizations that do use F#. I'll get to that in a point. Once again, like for people with C#, a way to deter them is to show them monads and workflows and the async stuff and everything. And in that regard, you immediately cut off all the low-skilled development that would. There is, I guess, another issue here of people being able to actually sell their development time in F# because whoever is ordering, they might have a bias. But I think it's secondary. I think one of the biggest problems is the perceived lack of evolution, in the sense that you look at like what's new in F# 3. Okay, well, we've got type providers, we've got some improvements to the way properties are defined, and that's it, really. There isn't like a lot of stuff. But then again, the counter argument is that there isn't much stuff in C#4 anyway, or C#5, whatever. Because I mean, we had in C#2 we got generics, in C#3 we got LINQ, which was awesome, and then it becomes boring. But you do see that okay, F# made it into Visual Studio. That's a fantastic achievement for Don-Sign, but kind of stopped at that point. So there would be some, I guess, for most people, there would be some skepticism as to where is it going. And most of the people I talk to, well, lots of them just say, oh, we're too busy with our daily lives to learn all this stuff and to actually apply it. So I want to talk about maybe not so much the generic F# as in let's go out to the masses and let's talk to everybody about moving from C# to F#, but rather about the very narrow, the very domain-specific, perhaps functional, but I wouldn't even sequester it that way. The very specific domains where F# is actually being used today. So from what I see, it's used for DSL design. I'll show that. It's used for math, which once again a bit surprising because to be honest, I mean, mathematicians, strictly speaking, they shouldn't care so much about the programming languages because they've got their computer algebra system. So why F# and why not C++ or whatever. Then there is the kind of more things more to do with the way that programming constructs are defined in F#, and specifically symbolic processing. So you've got something that needs to be parsed, interpreted, given some form. The argument for all of these is, of course, yes, you can do them in C#. Yes, you can do them in C++ even. But I guess it's made somewhat easier, not so much by the functional nature of F#, but by the corollaries. So by the constructs that serve functional programming, but they're also just unique in themselves. So let's start with DSLs. Why is it interesting to do DSLs in F# specifically? Well, one reason is that you can do top-level declarations. So in C#, at the very least, you need to have a namespace, and you need to have a class, and you also need to have a main method. So that's 3 levels of nesting. In F#, of course, these are optional. Of course, they're implicit. So when you compile everything, you do get all these constructs, but you don't have to write any of this stuff. So no need for a main method. Then there is the invocation for curried methods, which doesn't need braces or commas. So you've got a curried function do_foo, which takes 3 arguments. You just write do_foo a, b, c. You don't write do_foo open round brace a, comma, b, comma, c, close round brace, semicolon. I should have added lack of semicolons to the classes. Then there is really no need for. Okay, so you're sitting at the top level. There's really no need for explicitly declaring variables at the top level. I mean, you can do it, but you can have something that appears as global state. You know, like if you're in C and you define a global integer or a global type, it's just everywhere. You can use it that way. It's actually the reason why it's good is because when you're working with a DSL, you don't have to keep writing let p equals new project, p.members. Whatever. That's not the way DSL should look. And the end result, if you put all of this together, is that you effectively end up writing something that's close to English or whatever language you're comfortable with. And the only real caveat of it all is that because you're using typically when you're doing this kind of stuff with top level definitions that you change, you do get mutability in the book. So let me show you how this looks in real life. I want to show something from the good old days where I was managing projects, and I essentially had to perform. And this was, like when you estimate a project, there's 2 ways you can do it. We can say, we're doing it the agile way, and which is going to have a time and materials estimate, or you can do it the really kind of waterfall, old-fashioned fixed price way. And this is that variety. So I did warn that mutability is ugly. This is the way that you define public fields. I think it's a bit nicer now in F#3, but it doesn't really matter because, as I mentioned, as soon as mutability comes into the picture, then you get problems. So what's happening here? Well, somewhere at the top level, I defined a couple of structures for projects and different task groups, different tasks within the groups, and different resources, meaning people that can develop them. And then I just create a global-looking mutable construct called my project. And then I create a couple of DSL constructs. So essentially, something it's just a function. It's just a function binding. So it's something that takes, when I define a project, I write project foo, and then there's this starts key thing. That's actually a parameter that's completely ignored. We don't care. Because we want to say that the project foo starts on this particular day. So the starts on part is completely meaningless. So we essentially ignore it, but everything else is recorded in this global-looking variable that we have. And then we have these numeric definitions, which are also just placeholders. because we're trying to get as close to English as possible, so we have definitions like with rate equals -1. All of these are just filler elements for the DSL, because you want it to appear as English as possible. And this is why we also have definitions like let hours equals 1, let hour equal 1, almost the same thing. And once again, you would see parameters like this is a key. That also means that we essentially ignore it. I should probably scroll down to the place where the DSL is actually being used. So from here on out, this is something that you would actually write yourself. Everything up there you would just use from, import. So I have a project called Write an F# DSL article. It starts on this particular date, and I need two resources. I need myself, I'm a writer, I've got a certain rate, and then I have a computer, which is a dumb machine that doesn't get paid anything. And then I have task groups. So I have this task, this task group, bunch of tasks underneath it. Obviously, you will see that there is no scoping here. I'm not having like a group and then curly braces and tasks within it. It's kind of an in-order thing. So as these things get executed, they get added to some list. It's all kind of implicit, but the end result is I say, okay, prepare my project. And let me run this. This better not fail, because it actually creates a plan, I think, of some kind. Come on. So, very simple. This is something that we would typically package up and send off to the client, and then think about it again and again, and change it. But we would change it in the DSL. And why would we do that? Because all this crap is not conducive to how programmers think. I would not be sitting here and dragging these little lines around. I may be a project manager, but I still think this is a wrong way to go, unless you're already in the project, in which case it makes sense because you're adjusting something that you've already committed to and maybe got some money for. But when you're just thinking about it, that's the way that we handle the estimation. Obviously, in a lot larger scenarios than this one. So this is an example of how you take an F# DSL and if we disregard everything up top, this is something that a project manager with hardly any knowledge of programming could write. And in fact, and I'm sort of diverging here, but one of the projects we have at JetBrains is called MBS. I don't know if you've heard about it. It's essentially a toolkit for building DSLs and for letting people work with those DSLs. We actually have an implementation of a workflow editor for our backtracker done in this specific format. Let's see if I can bring this up. Eventually, I'll just open up so many programs that the whole thing will crash or something. But it should be interesting. So while this is loading, the idea is, once again, very simple. You take a language and you drag it as close to natural language as you possibly can. Now you don't really get any verification done at this stage. I guess this is something that people could write as a separate kind of thing. Okay, so the workflow editor will load at some point. I'm going to continue with the theme. All right, so that's DSLs, one of the examples. Okay, so next area of concern is parsing indexing. Why is it great to use F# to parse things? Well, actually, if you work with F#, you're already subject. You're already a victim of exactly that. Because what's happening, and F# is open source, so you can visit the link. And what happens is the F# support for Visual Studio, it actually parses F# using F# and does perform some kind of check. Specifically, the type inferencing. And in fact, in the future, when we do come to support F# and U#, the type inferencing will probably be done in F# because it's the right language for it. But anyways, F# comes with a toolkit, FSLex and FXYAC, so you can build your own parsers if you need to. But really, it's not about that. It's more about the language features and how you get their power and leverage it for parsing specifically. So the kind of things that you have is, first you get discriminated units. So essentially, instead of building a classical type hierarchy, you can very quickly make this one huge chunk of different structures that represent different tokens. It's very simple, and you're not building whole classes fully featured. You're just building these tiny little constructs. The second thing is pattern matching, things like partial matching. Obviously, you've parsed your construct. You've got your complicated definition into some kind of tree. What do you do with a tree? Well, you want to go through it recursively, do something to it. I'll show an example of exactly what I mean. And of course, the whole business with list comprehensions. Even if you're not explicitly using lists, you're still using the the match constructs and the partial matching. And you can take, you might have a string instead of a list, but you can still massage it into the right format to get the pattern matching and the things like, if you have a match against several elements, you can take two of these elements and say, oh, this is a new pattern, and then match against that kind of stuff. So let's do another example. As soon as this comes back online. Oh yeah, by the way, this is the workflow editor. Never mind the weird-looking stuff. I'll try to explain what this is and how it works. So this isn't F#. This is a DSL that I'm using. So we have this bug tracker, U-track, and in addition to being able to work with it directly, you can also define lots of rules for it. So I use it as an accounting system. I travel a lot, and I need to keep tabs of where I've flown, taxis, crap like that. Typically 4 currencies that I keep track of. So essentially, what I get as a customer is a tool that lets me write various definitions using a specified language, using a specific language that is geared towards bug tracking in this case. So this DSL, it already knows about the types I have in my system, and it does things like completion. I can't demo it because I'm not connected to anything, but the idea is exactly the same that I've shown with F#. So you just use a simpler programming language that, well, in this case, it's a bit like a mixture of maybe Java and English, but in the F# case, it's just almost English. So let me show you the parsing and lexing. Let's jump here. So I had this idea. When I was working for a company, they did process control. And they basically gave us a 200-page Word document full of math, so formulae. And they said, oh, guys, can we have this in C#, please? And I was like, okay, well, it would take a few months, maybe. And then the idea came, sort of, you have your formulae. They're defined in the Microsoft Word document, but you can actually get them in a structured format, because you can export them as MathML, which is XML, effectively. So you have your formula in XML, which is great. But then you need to parse them, and you need to build something out of them. And in this case, this something would be code that you're ready to compile. So I'm going to deliberately close some stuff in order to maybe not explode the system. Let me see. Struggle with running too much stuff just before a presentation. Always a bad idea, but load, come on. College project. Alright, I'm gonna jump back in. So I wrote the tool. I decided that I would write a program which would essentially take care of it for me, because I'm not spending several months translating from math to C#. So effectively, this chunk of code is a part of a discriminated union for the MathML types. So you've got your formula, you convert it into some kind of XML. You want to parse it. In F#, you can simply define this kind of, and this is a recursive structure, by the way. It's a type expression, but it can have constructs which are themselves composed of expression lists. And this handles all the obvious things. So, like for example, MO is an operator. MRoot is the root of something. MFrac is a fraction. Subscript, superscript, square root, specifically different sums, for example, different types of constructs. You write this instead of doing this massive hierarchy, or building a commercial grade parser, so we say. And then if we go into the place where we actually parse this whole thing, what you then do is then you simply what I did here is I just made a map from the string name of an XML element to one of these discriminated union cases. And then I can just take a huge chunk of XML and I can recursively parse it. There's a lot of stuff here, but essentially you, through very clever list or array manipulation, you grab each XML element, you take its parameters, look at what it is, and you recursively build from an XML construct. You build an abstract syntax tree effectively. Let me show you the end result. The actual app is very boring, I warn you. And I'm going to fire up Word as well, just to make it more fun. Alright, let's actually going to go, yeah, this is the app, nothing to it. I'll reopen it in a sec. Let me open up something that already has a formula of some kind. I think I had a special one prepared just to impress everyone with how complex things actually got in the real world. Unfortunately, I can't show the formula that we had to translate, because it turns out you can also patent formulae and have copyright on them, to the effect that people can't even show them in the presentation. But, no comment. Alright, projects. Alright, so it's some equation of state, so it might be iterative, I don't know. You have this formula, you need to do it in C#. It's easy, but it would take silly amounts of time, and you will make mistakes. And you have 200 pages in a Word document with these formulas. So essentially, if you kind of look around, you'll see that Word is being friendly to us, and it's letting us copy the whole thing as MathML. So I kind of get to select everything and just copy it. And then there's my little app. So I paste it here. There we go. It's rather long. Maybe I don't want Greek identifiers. Let's do it Roman. So that's what it actually does. This is F# syntax tree. It takes XML in, parses it, outputs as C# or if you want F#, C++. C++ doesn't work. Never mind. The joy of presentations. So that's what was actually built. And let me show a bit more about the kind of stuff that I'm doing in here. So we get this this whole huge set of types, and then we actually go through this top-level expression recursively for a particular language, and we say, I want to print it. So we have a printer of some kind. This is actually a huge chunk of code, but I'll just show some arbitrary location. So for example, here using list comprehensions, I can say that, you know, if I have something followed by an operator, followed by something else, followed by an operator, followed by something else, then what is it? It's an AX plus B construct. And the great thing about AX plus B constructs is in many cases, like on the GPUs, for example, they're actually optimized. They have a separate instruction called MAD, not because it's crazy, but because it's multiply and add, and you can optimize it that way. So because what this program does, it doesn't just translate math. If it translated math straight away, you would have something silly. You would have something like somebody wrote x squared, and you translate it to math.how x comma 2. And this is totally the wrong thing to do, because this is Taylor series expansion in math, so it's stupidly slow, like maybe 100 times as slow or something. So you write x times x. But in order to be able to do this, you need to analyze this whole thing. So if I jump back to the program, for example, we have a parameter for maximum inline power. So this essentially controls how many power functions get turned into multiplications. So for example, here I have rho to the power of 6, and at the moment it's not that great. But if I say this is going to be 10, you can kind of see what happens here. So it gets inline. There's really no great solution to problems like that. I actually have a whole separate presentation on the way that you can optimize the math that you can translate. And once again, this is all possible simply because of the list comprehensions, because of the way that we can process all this stuff. And yes, strictly speaking, yeah, you could write it in C# or generate via C++ or something, but it's just so much more convenient to have this nested match structure. So for example, if there are many ways to define the constant e in MathML. This is an exponent, this is an exponent, funny looking one, this is an exponent. So when we see an e, we have two options. We can leave it as is, or we can replace it by, I guess, math.e or system.math.e, that kind of stuff. But we need to know when to do it, and we have our three cases, so we check against them, and then we look at some of our settings, and if we're using if we're translating for GPU.net, which is I think a dead project now, then we do this. Otherwise, we'll look at which language we want to output, and we kind of we write it out. And same goes for pi and stuff like that. And there are lots of nuances, and I guess truth be told, you would never have a perfect translation from math to F#, but you can get very close here. I'm going to jump back to the presentation. So parsing is an interesting choice, but strictly speaking, as I mentioned, we kind of have a side project for supporting F# and V#, and we're not going to do parsing in F# or we'll use C# for that. Partly because the whole infrastructure of V# that we have to plug into, it's all object oriented anyway. So we're going to stick to what we know rather than doing it the nice way. In a computer algebra system, you can reuse variables, but that's, I don't know. If you're a pure mathematician, you're not thinking about reusing a variable. So in the sense that if you define, if you define x1 and x2 as the solutions to some equation at some point, you would not be reusing them to say, oh, by the way, now x1 is equal to something else. You would choose new variables. And so this is relevant because F# kind of maps onto the concept. It kind of connects to this idea, which I guess for programmers is a bit difficult to grasp at some point. Type inference, so V# with guessing your types. It generally means less typing, although it can trip you up a little bit. Like for example, 2.0 times sine of x is an invalid F# construct because sine returns an integer, and you cannot multiply the double by an integer. You can't do it. You need to cast the integer to a float explicitly. So we would write either float sine x or sine x, you know, bar float, whatever you prefer. But even so, you know, the level of noise gets decreased. Then the whole thing is with no braces and function calls, which some people also position as a kind of advantage to F#, but I actually find it a little bit dubious because in math we do use braces. You know, if you call a function in mathematical notation you do open a brace and you say x comma y whatever. So the argument here is not as solid. And then the whole business of functional composition, which once again people kind of try to promote as, you know, this improves the this improves the experience. But once again, I have a counter argument. Functional composition, as in being able to write, you know, A, B, something like this, is great. But it really makes sense for more for symbolic computation than for just calculating stuff. Meaning that if you want to differentiate a function, for example, okay, it makes sense. These kinds of things. But the problem with symbolic computation is if you need symbolic computation in F#, like, I don't know, differentiation, integration, that kind of stuff, you basically have to write it yourself. It's not built into the language, just like most things aren't built into the language. You get simple computation. You can take a square root of a real number, or you can take the square root of a complex number, but you cannot compute an integral, or I don't know, any of that stuff in F# by default. I don't know, maybe libraries exist, maybe they don't, but moral of the story is, yes, people position functional composition as a kind of, you know, a benefit, but once again, I'm not that convinced. And you just see that I haven't missed anything here. Oh yeah, crap, I was going to mention who actually, yeah, why is it that we don't have reliable info about who uses F#? Well, the reason is because these guys use it. These are basically quant finance institutions, so people who are doing financial math. And the reason why they're doing F# is not because they want to have fun. They're not like me. They're using F# because they see some strategic benefit to it. And because they see there's a strategic tool, they're not really talking that much about it. So a huge chunk of the quant world may be using F#, but we'll never know. So these are the companies that have come out, so to speak, and said that, you know, we have some programmers using F#. Some of them offer real you know, numbers on how many people are using it, but it's not a clear-cut picture. And from this you see that, oh, you know, this F# language is used by some financial math nerds. I don't do any of that stuff, therefore, you know, why should I be bothering with the F#? And it's particularly more amusing considering that the world of quant finance essentially revolves around C++. And due to some of these options, plus the fact that you get access to the whole of the .NET ecosystem, your choice might be driven towards F#. And one of the motivators for doing it is that banks and quant institutions, they are reliant, at least in part, on Microsoft technologies. So they might have things like ASP.NET, they might have WPF client applications for their traders. They might be using something like BizTalk, for example. So for them to use a .NET language kind of makes sense, and they go for F#, accepting all its deficiencies and reveling in its advantages. So there is no real There is no real story for, oh my god, let's take everything, all the Corn stuff that we have and drag it onto the F-sharp platform. But there is a story for taking small things, or at least things which are applicable, like math-related or logic-related things, and dragging them over to this language, provided, of course, and this has lots of assumptions, because keep in mind that it's still very much a C++ world. Most people, they learn C++ and their job interviews involve C++, and everything is C++. Therefore, it's interesting that people would go in this direction. So let me start with something simple. So this is essentially a simple trading robot for basic types of arbitrage on options trading. I don't know if it says anything to you, but never mind. So in most of the civilized world, a trading calendar is fixed each year. Like we know that there are typically 252 working days in a year in the United States. Unfortunately, in certain countries, like Russia, for example, damn it, the calendar changes each year, and so you need to keep track of what when the holidays are. A simple task, right? You could write all of this in C# or in C++ or in any other language, but just look at the clarity of this. So you've got the daytime. Grab the day of the week. If it's a Saturday or a Sunday, then unless there's these two exceptions, it's not a holiday. Otherwise, look at the month, and then depending on the month, check the day. Simple as that. This, I guess, this illustrates not so much the math, but actually the algorithmic part. So once again, nothing magical is happening here, but this saves a lot of time, because I could do this in a C# with a switch statement and a couple of if statements. I mean, no problem. And in fact, some people actually implement pattern matching in C# using various chain extension methods and extension method chaining, that kind of stuff. And it works. It's just not as awesome, I guess. So let me dig around. Here's another thingy. So when people write things in mathematical notation, things that we typically define with ifs, they kind of they go something like this. They say, let's say f of x equals, and then they do this huge phrase like 1 when x is greater than 0, and I'd say minus 1 otherwise. They don't say if x is greater than 1, then whatever. They don't write lambdas in math journals. And when you come to actually translate what they've written, and this is exactly what I'm showing here, when you translate what they've written like this, it makes a lot more sense in F# than it does in C#. And then you can see a rather convoluted example. So this is something that, given that you have 4 different volatility values, it reduces them to just 2 values based on some logic that basically you can read in a paper and just replicate it from there. I would not say necessarily that ordinary kind of math, like the math you see here, is any way better in F#. The only thing, of course, yes, instead of writing math.exp, you just write x. I suppose you could have, you can create extension methods for that in C# as well, fair enough. For the most part, yeah, little things like being able to pattern match against an array. So I have an array of floating point values here. And I actually declare something that looks like an array with named members. And I say that, oh, by the way, you know, args is an array, and I want to grab that array. I know it contains 6 elements, and I want to assign them to the values S, A, B, C, D, E. You can't do that in C# or any language using one line. So these are some of the niceties that you get out of it. And I guess the other side is that array graph is not so nice. I don't know why I need to be writing a dot here. And also, if you look at arrays in languages such as MATLAB, for example, they're a lot more powerful anyway. So it's not like F# is being designed with math in mind. It's just that, yes, some things are kind of nicer, but just from looking at this, you wouldn't necessarily surmise that this is like a major selling point. It's just a little easier for the math types to understand something. So here are some very simple option pricing. Nothing major happening here. So yes, you do have little silly things like using functional constructs to encapsulate all your parameters into an additional construct. I guess it's a closure reversed, which is why here, even though this is a function applied to these arguments, it looks like it's the other way around. It's the kind of stuff that you do in F#, and I don't know if I like it really, because ideally in F# I would have a construct saying, you know, take these parameters and put them into a tuple or put them into a list, whatever. I don't care, because I just want to use them all over the place. And that way I cannot. And yes, strictly speaking, yeah, you do get some benefits from functional composition. So like here, so a way to encapsulate the idea of all parameters. We don't, but it's still nice. You know, I have a pricer, and then I have I want to specialize the calls. So from a C# perspective, it would look like two additional functions for calculating call input from the price function. Once again, tiny little thing, maybe not much, but it's nice to be able to do it this way. And here is a demo of maybe where things are not so nice, because some mutabilities evolve. So these are different ways of, let's do this one. These are essentially different ways of finding out the implied volatility of something. So it's a numeric method for locating a particular value. And it's iterative. It runs lots of times until it finds the value or it craps out, whatever. And here we need things to change. So we have this whole business of mutable, and we have generally when mutable things come into view, it becomes a problem in F#. When null comes into view, it becomes a massive problem in F#. But luckily we try to avoid that. But mutability by itself, I think it's actually illustrated better here, that you have stuff like this as a breakout condition. That's kind of maybe not very nice. And also remember, I mentioned the ability to call functions without braces. So for example, function f applied to a, kind of being written as fa. I don't know if this is nice or not. I think it's actually, in certain ways, it's confusing, and it's somewhat non-mathematical. So maybe I should be writing it as f of a instead. But once you see this option of writing like sqrt of t, or like here, for example, cumulative normal distribution of d2, you suddenly, realize, wow, they gave me this option, let's use it. They gave us the option to use a single dash inside an identifier, and you can actually have more than one. You can have 10 dashes in an identifier. So let's use it, even though it's in this case it's totally appropriate, because n dash is exactly the right thing. So n is the integral of n dash. But in most cases, people would abuse it. Like I have abused it in that estimation DSL, by the way. I used it just as a kind of saying that I have a value x, and then I have a new value of x, so I write x dash, and then I have another value of x, so I write x dash dash, which once again is kind of arguable.
Do you have there any reason to avoid recursion?
Do I have any reason to avoid recursion? I don't know. And in actual fact, the funny thing is, these algorithms, a lot of them, they're already out there, and you just grab them and you go to the best of your ability to copy them. So in this case, maybe not. But once again, it's it really depends on the situation. I guess it depends on what kind of iterations you're doing, and this is just a very simplistic algorithm. This one, and it fails in certain cases. The bisection method fails given certain starting parameters, and even the Newton-Raphson method fails. And actually, you know, you'll see that I'm doing some checks here against NaN and infinity because iterative methods, they can just diverge. You know, let's suppose that, and this actually happened. Let's suppose that you've got some bank or somebody went crazy, and they're actually selling something below the market value, below the theoretical market value. And when stuff like this happens, your models, well, most people's models generally can't handle it, because you start getting something like, I don't know, negative volatility, for example, or whatever. So you have to handle these crazy cases because this thing might not converge to any value. So sad but true. I'm gonna continue with the whole thing. Okay. So, yeah. So nice. So talk a bit about F sharper. There's actually one more thing, one more demo that I want to show. But for me, parser construction is, I mean, I can build a parser for MathML, but this stuff is, you can imagine, is a lot more serious, especially considering that F sharp has like a gazillion operators. So I'm not gonna mention too much about that because, to be honest, you know, when we get something that we can show, then we'll show it. But until then, I want to show one more thing, just briefly. So F sharp, it actually, as you know, it supports REPL, so you can sort of type in stuff and it gets executed immediately. And it's something that computer algebra systems also value. If you go to like MATLAB, for example, you type something in, it gets executed immediately, and you get some state that gets preserved. So let me open up another project. So compilation, regardless of the language you use, it takes time and it can become rather annoying. So what I did is I essentially wrote a little app that, this one, let me wipe that out, a little app that continuously compiles or continuously interprets, however you want it, whatever you type in, and it basically lets you do a kind of procedural REPL in a way. Let's see if this picks up on the. So yeah, I printed that. Fine. Well, so the idea is that you're working on an algorithm, and you want to see what's happening. And I actually, I'll actually do a proper demo of this one that I had just before I deleted it. So the idea is, I don't know, you want to solve a quadratic equation. So you're right. Let's solve quadratic ABC equals, and then well, I guess you return x1 equals 0, x2 equals 0, and you return almost C# reflexes here. Return x1, x2, and then you foo equals solve quadratic on some values, and you try to print it out. No, actually, so you try to print something out, and then you realize that you're completely wrong. Everything you're doing is trash. And at this moment, you might be pressing F6, or you might be just generally unhappy with you know what Visual Studio gives you, and it takes at the moment it takes too much time to just try to get your head around what is actually going wrong, like what are all these stupid constructs. So this tool, it lets me actually kind of write things as I go, and I keep getting different errors all the time, and I can kind of tweak things and see, you know, what's happening, and eventually at some point I start writing actual code. So I would say that, I don't know, let's do a discriminant of A, B, and C. So B times B minus 4 times A times C, and then, well, I guess the great thing about F# is you can pass operators as parameters. So I would say let's solve for an op equals minus equals, let's say, op minus a plus or minus the square root of the discriminant divided by 2 times a. Everything I'm typing here is more or less wrong, as you'll see in a moment, and then the solution is you do it with a plus. So solve plus, and so the fact that it actually prints something out is pretty bad. So it's totally not about solving quadratic equations. It's about the fact that you can take a chunk of F#, you can feed it to F#, get the result straight away. Change something, feed it, get the result straight away. The performance of this for debugging tiny mathematical functions is good enough. It's instant. You know, you change something, and you see it updated within a second or two. So it's something that I actually use to sort of speed things up, I guess. So coming back to the conclusions, if there are any conclusions, I'm sure that there are unique conclusions to your case as to how you can leverage the whole F# thing. But so F# is okay for math, but really the reason why computer algebra systems exist in the first place, why everything isn't done in C++, is because of libraries. And a corollary of that is the fact that for some of the tasks we just want stupidly high performance. And in this case, once again, F# might not be the best solution. I know, you're solving partial differential equations numerically. You probably, if you have Teslas or, I don't know, any kind of GPUs, you might want to do it there. It will be much faster. And once again, the F# is a language that doesn't have a good GPU story. C++ does, because you get it. I mean, in the Microsoft compiler, you get C++ AMP, but you can also get CUDA toolkit with Nsight and everything. You would have to go back to Visual Studio 2010, but not a problem. So F# is great for algorithmic or backend kind of tasks, like the ones I showed with calendars and with taking kind of different logical calculations. And I guess people use it for things like circuit verification, so things where you don't really need to do that much computation as much as organization in a very tightly contained kind of domain. It's fairly useful for DSLs. I wouldn't say that this is a deal breaker by itself, because typically the kind of things that people would want it for is maybe building view engines. And in fact, there is a tool called WebShark for F# that tries to be the front end and the back end written exclusively in F#. So you write HTML using F#, you write everything using F#, and there is a tie-in between the front end and the back end. So you can have an F# function on the client calling an F# function on the server. They just have different attributes. Obviously, lots of reprocessing magic going on behind the scenes. It's fairly good for just quickly defining simple data structures. As soon as data structures get complex, well, that's where the whole beauty of ReSharper and the stuff I've shown comes in, because you might need to generate those comparators and whatever. And again, the stuff it's not so good for. So if you're into object orientation by itself, then F# is just tedious. And keep in mind, like in C#, for example, if you're implementing an interface, you can tell reshaper, just generate the whole thing. In F#, you would maybe take 10 attempts before you even implement it correctly, because there is no help. You're not getting any help from either Visual Studio or anywhere else. So you have to know the exact syntax, and in some cases it's rather ugly. In fact, one of the really big questions as to should we bother doing V# or F# integration is well, strictly speaking, most of what reshaper does, it relates to object orientation. Viewing hierarchies, navigating between classes, that kind of stuff. It all makes sense in an object-oriented environment. And typically when people do stuff like quant finance, for example, in F#, they don't care about any of that stuff. Because, well, can we imagine that a cubic equation inherits from a quadratic equation? I don't think a mathematician thinks that way. I don't think that people even if they see some duplication or some ways for building hierarchies, I don't think people really do it that much. They do it in the quant context. They do it on the market side. So you would have like a futures instrument, and then you could have an option, option on that future inheriting from the future. I suppose that makes some kind of sense, but for a purely mathematical construct, it doesn't make so much sense unless, well, strictly speaking, arrays are objects in .NET. So kind of like the F# list is not something you would necessarily be doing in a high-performance setting where you got a huge amount of stock data and you stick it into a list. If you actually look behind the implementation of the F# data structures, you will see that some of them are horribly inefficient, some of them are actually doing constructs one through another, and it's kind of hit and miss. So I imagine that for a certain group of algorithms where you really get true tail recursion, where everything works smoothly, that's fine. But in the real world, like for example, you get lots of stuff from a certain stock market, and it's typically like an order book. So it's a mapping from some kind of ID to order volumes, like bid and ask order volumes. And in C# you use something like, I don't know, sorted dictionary, that kind of thing. In F#, if you were to start using the F# constructs, you would lose the efficiency. You would actually not be able to trade. You would simply not have enough time, especially if you're trying to process a huge chunk of the market on a single machine with a. And I know there's lots of talk about things like the LMAX disruptor and the whole bloom buffer concept and the way that gets fit in, but in the real world, I mean, the kind of processing that goes on is a lot more complicated, because essentially, like, I don't know if you've heard about LMAX, but they're a forex thingy. So essentially, they just match orders, and for order matching, yeah, you can get several million transactions in a second. If you're trying to build an order book across a couple of different instruments, let's say a couple of different options, each option would have, I don't know, 20 calls and puts, so that's 20 times 20 of these sort of dictionaries. You get data like once 100 milliseconds, you get maybe like 40 records. It's something you do, and you need to do lots of computation on all this stuff. You would maybe avoid the F# data structures for the most part. And finally, the whole UI story. There is no UI story for F#. I mean, some people are trying to do things like, oh, you can build in WebSharp, you can build a whole HTML page just from using the F# constructs. They literally have things like, you have your table, and then you have a square brace, and then you have a table row, and you have square brace, and then you have a table cell, and then you have a square brace, and then you have a paragraph which has a text equals something, and all those wonderful square braces. That kind of stuff, that's available, but I don't think that's a solution to anything. I think that the ecosystem that we have right now for building UI in WinForms and WPF and whatever is good enough, and it can talk to F#. And actually, surprisingly enough, it's really difficult to find real problems with interfacing between the two. I mean, obviously, if you're using F-sharp specific data types, then they marshal across in a really ugly way, and you might not get something usable. But overall, I would say that I'm sticking to tiny little WinForms applications that, because I mean we have things like DevExpress which have been doing WinForms controls for like 10 years or something. They're pretty good. They're pretty good. They might not be the smallest or the most performant, but really the front end, the story is already kind of told. So if somebody comes up with something nicer in F# or in a functional construct, but I don't think UI is a functional construct. I think it's an object-oriented construct. So you have a window, and that window has a whatever, and so on. I guess it's a matter of perspective. So that's it from me. Twitter, email, questions.
Well, I'd like to ask about this UI thing. So is it, did I understand correctly that if you have a kind of backend in F# and then a user interface in C#, and you can compile them to a single executable?
Well, no, they compile to separate DLLs, but they talk to one another just fine.
Okay, but how does that communication go under the hood? Is it like, do they execute in one process or?
No. All the assemblies still get loaded into the app domain of the originator. If you have a C# project and you add a reference to an F# project, you get IntelliSense, you get all the good stuff. So absolutely no problem. There are certain cases where you get things not showing up in IntelliSense, and you get certain obscure bugs, but you really have to work a lot with F# to hit those kinds of cases. In most cases, it's just it's fairly obvious. And in fact, the whole domain of what you would typically do from C# in F# is very small. So in F# you would have say a module with a couple of functions, and in C# the way it looks is a static class with a bunch of static methods. You just write module name dot whatever. That's it. Of course, you can go the whole. You can make classes and interfaces and whatever in F# if you want to, but I don't think that's the idea. I think that it's the support for object orientation is secondary. But if you look at the way it looks, if you I had a file from maybe this one. No. No, let me dig up a file from the actual construct. Okay. Now this is actually a good demonstration of how data structures defined in F# look. I don't like. I like the simple type definitions, but I don't like the full definitions because they just look monstrous. But I had something even uglier. I'm trying to find it now. No, I don't think I'll find it. It's a typical talks curse. But essentially, like for example, sometimes you get the soft market actually gives you an API or gives you a generator for some kind of API. And many of these are actually, you get a C++ API, and then you get lots of bindings on top of C++. And they look kind of manageable in C#. Well, because a lot of it is casting to struct pointers, which is ugly by itself, but in F# it just looks totally wrong. So, not a big fan. All right. Any more? Yep. Thank you for inviting me.
Thank you.
I hope it's not the last of my talks in Helsinki. I actually go through. I travel between Stockholm and St. Petersburg all the time. So I show up here often, but for some reason I've never given a talk. Hopefully should be corrected. Actually, I'd be curious to find out if there are any conferences or large-scale events, that kind of stuff here. That'd be awesome. All right, thank you.
Thank you.